All right, the last one we're going to do is the fifth degree polynomial. So I'd like you to do some predictions on your own on this one. So you can pause the video and go through the next few slides. Go up to slide 32. Let's see, so you can make your prediction of your fifth degree polynomial. I know we haven't graphed that yet. You can do an XY table, or you can try to make a guess. And then on the next slides, you'll do some exploration. And let's see. Let's come back together on slide 32. So why is this so big? There we go. I don't know why it's being weird. So work through slides 26 to 31 independently and then come back for slide 32. So go ahead and pause and work through 26 to 31. All right, let's go over to slide 31 now. 32, sorry. So on slide 32, we're getting to the second part. So our first part, we just spent a whole lot of time exploring a lot of different polynomials. So now I want to formalize those or observations and see what connections we can make. So first question, how does the leading coefficient affect the graph? So our leading coefficient is A. That can't be equal to 0. If it were to equal to 0, then that first term would go away, and that would no longer be a linear, it'd be constant. This would no longer be quadratic. That term would go away completely, it'd be constant also. This would go away and it would become linear because the next term is an x. So A can be anything but 0. So right here we have a purple function as a linear, we have the black function as a quadratic or a second degree. The red one is a third degree polynomial, the orange is a fourth degree. We could even do, I don't know what else we could do. We can add a fifth degree polynomial. Let's see, can I change that color? I know I can change the color, but I can't seem to remember how. How do I do that? Anyway, so what happens as A is negative? What happens when A becomes positive? How is A affecting these graphs? So you can look at one graph at a time and see how A affects that one. Or you can look at two graphs at a time and see how A is affecting these two graphs. Or you could look at just the graphs that have even degrees and see how those are being affected by the A. Or you can look at just the odd degrees and see how those are being affected. So what do all graphs with a positive leading coefficient have in common? And what do all graphs with negative leading coefficients have in common? So I'm actually ask you to pause and type up your own response right here. You can see my response is already here, that the graphs with negative leading coefficients are reflections over the x-axis of the corresponding positive polynomial. So pause, and once you type in your own response, go ahead and submit to class. And then let's go to slide 5. And here we're looking at how the degree affects the graph of the polynomial. So here we're looking only at even degrees. So what do these graphs all have in common? And I can change A, right? We can go negative, we can go positive, but what do they all have in common? Go ahead and pause and play around with your graphs and see what they have in common, and then come back. And then type in your observations here. I wrote down my observations. I observed that all the graphs have the same end behavior on both sides. So the left, the purple graph is going up on the left, so it's going up on the right. When A was negative, then the purple was going left, down on the left and down on the right. But whatever it does on the left, it does on the right. That reminds me of a parabola. So all those even degreed polynomials follow that same end behavior as x squared. I kind of want to add that actually to my response. So all even polynomials follow the same end behavior as y equals x squared, or a parabola. I'll share that. All right, once you type up your answer, share to class, and you can hit pause while you're doing that, and then once you're done, go ahead and hit play again. So we're still looking at the degree and how that affects the graph. We looked at even on the last slide. Now what happens when with odd degrees? So we noticed with the even degrees, the end behavior was the same on both sides. I can look at one graph at a time and see my end behavior is in the opposite direction now. So on the left, it's going up, and on the right, it's going down. Whoops. And then when my A goes positive or negative, it flips. So when A was positive, it's on the left, it's going down. On the right, it's going up. And vice versa when it's negative. So is that true for the other graphs too? They seem to be following that same pattern. In fact, they all follow the same pattern as x cubed. Is that true for when my functions get really big, like a 13th degree and a 101st degree? They all have that same pattern. So go ahead and pause and play and look for your observations to enter into the next slide. And when you're done playing, go ahead and push play. Okay, so the common behavior of these graphs with an odd degree, they all have end behavior going the opposite direction. So all the degrees, all the polynomials of the odd degree have the same end behavior as y equal to x cubed. You can write your own observations right here and then click share with class. Go ahead and pause while you do that. And then when you come back, we'll go to slide 39 together. All right. So actually 39 and 40 we're going to skip over, and 41, 42. We're going to skip over points of inflection and extrema for now. However, in 4.2 we do talk a lot about zeros, so that's going to be coming up in today's conversation. So I do want to explore there. So take a few minutes. You can pause the video, take a few minutes, and explore how the degree relates to zeros. So explore how the maximum number of zeros relates to 0 degrees of polynomial. So you already did some exploring with these and finding how many zeros you can have. Look at the maximum, try to get each graph to have the maximum possible number of zeros. Like look at that blue one. As I'm sliding it up and down, I have no zeros, and then I have 3 zeros, and then I have no zeros. Oh, I'm sorry, 1. I always have at least 1. Right, 1 0, and then 3 zeros, and then I have 1 0. Do I ever have 2 zeros? Do I ever have 0 zeros? So look at the maximum number. So the maximum number we could do with sliding G around on the blue graph is 3. Is that the maximum? Can I get more by sliding, let's see, these guys around? Oh, see how that green one is now, and the blue one too. Actually, I want to highlight that. So let's look at the blue one now. So now I have 1, 2, oh, wait, let's move G, so let's move it up a little. So there we have 1, 2, 3, 4, 5 zeros on my fifth degree polynomial. Do you see any possible way to get 6? We were able to slide this down and up and change that to a 3 zeros or 1 0 or 3 zeros or 5 zeros. So what's the relationship between the number of zeros I have and the degree, the maximum number of zeros I can get and the degree? Let's look at that fourth degree function now and slide that one around. 1, 2, 3, 4. Right now I have 4. Is there any way to change these numbers to get myself more? Can I get 5 zeros with a fourth degree polynomial? So pause and play around and then go to the next slide to make your observation. And then I'll meet you on slide 44. So we're going to make a conjecture relating the maximum number of zeros and the degrees of a polynomial function. So I'm going to let you do that conjecture. So go ahead and pause while you make that conjecture. So this conclusion is actually going to lead us to the fundamental theorem of algebra. So this one's pretty huge, and you'll be hearing lots of this again. But regardless if a function is even or odd, then let's see, then the maximum number of zeros a polynomial can have is the degree. Is equal to the degree? Is equal to the degree. I'm actually going to put in, so that should have been something that you observed. I'm going to add in the maximum number of real zeros, because later we're going to learn that you could have non-real zeros that do not cross at the x-axis. But when it crosses the x-axis, that's how we count the real zeros. And the maximum number of real zeros of any polynomial can have is equal to the degree of that polynomial. So this green one looks like it's probably a fourth degree, 1, 2, 3, fourth degree polynomial. It's got 4 real zeros. We could slide it around so it only has 2 real zeros, but we could not get 5 if it's a fourth degree polynomial. All right, so that wraps up. I'm going to share that. The class time for this. I would encourage you to go to part 3 to check for understanding and explore those connections. And if you complete those future graphs, then I'll give you some extra credit for slides, let's see here, 45 through 54 to do independently.